Hi, welcome to my YouTube channel Electronics for Gate by Kota Venkanna. My mobile number 630-5826-909. In the previous class of transmission lines, I have discussed impedance matching devices. In the impedance matching devices, I have discussed quarter wave transformer. Today, I want to discuss stub matching in the impedance matching devices. So here, I want to discuss here about impedance matching devices. Before that, I want to discuss principle of impedance matching. So here, impedance matching, in the main our aim is to transfer maximum power transfer from source to the load. So here, as per the maximum power transfer theorem, how it is possible to transfer maximum power from source to the load? For example, so here ZS is the source impedance. ZS is equal to R plus J access. So then the load impedance ZR is equal to R plus R minus J access. So complex conjugate of input impedance. Then it is possible to transfer maximum power transfer to load. So this is the basic principle of impedance matching. So here in the impedance matching, basically two types are there. First one is quarter wave transformer, and the second one is here. Impedance matching devices are basically two types. First one is quarter wave transformer, and the second one is stub matching. So here already in the previous class I have discussed quarter wave transformer. Now I want to discuss stub matching. Here we want to discuss stub matching. So here, what is stub? A stub is a short section of a transmission line which is connected either in series or parallel to the short circuited or open circuited section of a transmission line. So here, stub is a piece of transmission line or a section, a small section or short section of a transmission line which is connected in parallel or in series to the main transmission line for the impedance matching. Then the maximum power is transferred from source to the load. Here basically types of stub matchings are two types. These are, first one is single stub matching and second one is double stub matching. Now I want to discuss single stub matching. So here this is the single stub matching. So in this single stub matching, so single line is this is the single line. So here this is main transmission line. So here this is ZS, input impedance of the main transmission line, and this is the load. The output impedance it is indicated with the ZR. So this is the short circuited. This is short circuited stub, a piece of transmission line which is placed in parallel to the main transmission line for the maximum power transfer to the load. So here L suffix T is the length of the stub, and L suffix S is the place of the stub from the load to the stub. So here the input impedance or input conductance that must be equal to characteristic conductance. Characteristic conductance, that is Zs is equal to Z0, characteristic impedance. And here the place of the stub is very important. So where the place is stub, the stub is placed, that place then that equal to at that place where the input conductance at that point is equal to the characteristic conductance of the transmission line, and stub length is adjusted to provide a susceptance which is equal in the value and opposite to the input susceptance value. So then the main susceptance of the main transmission line, so the total susceptance at this point must be equal to 0. For example, here 1 plus Jx is there. So this is the complex impedance. So then the complex impedance 1 plus Jx. The susceptance of the transmission line, that must be equal to minus Jx. So here the place at which the stub is placed, the susceptance, the total susceptance must be equal to 0, that is minus Jx plus Jx. Then the maximum power is transferred from source to the load. So this is the arrangement of single stub matching. Here we have to note down the main points. L suffix T is the length of the stub, and Ls is the length of the stub from load to the stub, that is indicated as Ls. So here we have to derive the maximum relation, the mathematical relation of location of stub. This is the L indication, location of stub, and length of the stub, Lt. So I want to derive the relation between Ls and Lt. So that is so here the relation between Ls and Lt can be obtained by the input impedance of the transmission line. So by using this equation, input impedance of a transmission line equation, we can derive the relation between Ls and Lt. So here the main input impedance of transmission line equation is Zs is equal to Z0 of Zr plus Z0 tan PL by Z0 plus Zr tan PL. So here Zs is the input impedance and Z0 is the characteristic impedance, and Zr is the output impedance, and tan P is the propagation constant, and L is the length of transmission line. So the derivation of this equation is very easy when the impedance convert into admittance, impedance values convert into admittance values. So this equation is derived in terms of admittances. So that's why admittance Zs is converted into Zs, input impedance converted into input admittance, that is equal to 1 by Zs is equal to Ys. Ys is the input admittance, Yr is the load admittance, and Y0 is the characteristic admittance. So this is by converting this equation into admittances, then the above equation is written as so here ys is equal to 1 by zs, that is equal to 1 by zs. So here 1 by zs is equal to z naught of zr plus z naught tan PL by z naught plus zr tan PL. So here again ys is equal to one by z naught of z naught plus zr tan PL by zr plus z naught tan PL. So here z naught and zr also convert into admittance values, then the above equation becomes. So here ys is equal to 1 by z naught of z naught plus zr tan PL by zr plus z naught tan PL. So here we want to convert impedances into admittances. So that's why ys is equal to z naught. Z naught is equal to 1 by y naught. Z naught is equal to 1 by y naught. Of here z naught is equal to 1 by y naught plus zr is equal to 1 by yr tan PL by, in the denominator zr, in the place of zr we have to place 1 by yr plus in the place of z naught we have to place 1 by y naught tan PL. So here in the numerator yr, this equation becomes yr plus y naught by tan PL by y naught into yr. In the denominator the above equation is becomes y naught plus yr tan PL by y naught yr. So y naught yr both are cancelled. So the remaining value is ys, input admittance. Ys is equal to, so y naught of yr plus y naught tan PL by y naught plus yr tan PL. This is the main transmission line equation in terms of input admittance. Input admittance ys is equal to, this is the y naught is characteristic admittance, yr is the output admittance. So this equation indicates the main transmission line or lossless transmission line input admittance equation. So why? Because the derivation of equations between LT and LS is very easy only by converting impedances into admittances. So that's why for the easy of derivation purpose we are converting impedances into the admittances. So here P is there, tan PL is there. P is the propagation constant, that is P is equal to alpha plus j beta. Alpha indicates attenuation constant and beta indicates the phase shift. So here in the lossless high frequency transmission lines the attenuation constant is equal to 0, that is alpha is equal to 0. So alpha is equal to 0 means P is equal to 0 plus j beta. What will happen? P is equal to j beta. So in terms of P, we have to substitute J beta. In the place of L, we have to substitute LS, length of the stub from output to the place of stub, that is indicated with LS. So here the YS source admittance is equal to Y naught of YR plus Y naught tan J beta. In terms of P, in term of P, we have to substitute J beta into L, and by Y naught plus YR tan of J beta L. So here tan of J beta, that is equal to J of tan beta. So that's why that value becomes Ys is equal to Y naught YR plus J Y naught tan beta L by Y naught plus J YR tan beta L. So here using the normalized admittance. So here normalized admittance means, so Ys by Y naught equal to capital Ys, that is normalized input admittance, and YR by Y naught. So that is equal by capital by R, normalized output admittance. So here this admittance convert into normalized admittance. Then what will happen? Ys by Y naught. Ys by Y naught. So numerator and denominator both are divided with Y naught. Then Ys by Y naught. This Y naught becomes this side. Then Ys by Y naught. To convert into the normalized admittance, Ys by Y naught is equal to YR by Y naught plus J Y naught by Y naught tan beta L by Y naught by Y naught plus J YR by Y naught tan beta L. So here YR by Y naught becomes capital YR, normalized YR. So that's why Ys normalized input admittance equal to YR normalized output admittance plus J Y naught by Y naught cancel 1. So then by J tan beta L. So here also in the denominator Y naught by Y naught that becomes 1 plus J YR tan beta L. So here this is the complex multiplication for the analysis purpose. Numerator, denominator value, complex conjugate of denominator value multiply numerator and denominator. So that's why Ys is equal to YR plus J tan beta L by 1 plus J YR tan beta L into 1 minus J YR. This is the 1 minus this complex conjugate of this value, 1 minus J YR tan beta L by 1 minus J YR tan beta L. So here multiplication YR into 1 YR into minus J YR tan beta L minus J YR square into tan beta L plus J into tan beta L into 1 J into tan beta L into 1 J tan beta L minus plus into minus J into J square into YR tan beta L into tan beta tan square beta L by, so A plus B into A minus B, that value becomes A square minus B square, but here J into J square is there, so J square equal to minus 1, so that's why 1 plus YR tan beta L whole square. So here we have to take common YR is common, so then we have to take YR is common in the numerator. Ys is equal to YR common this way 1 minus, so here YR is there J square tan beta L plus we have to take common J beta tan beta L. J tan beta L is taken common, so here J tan beta L 1 minus YR square by 1 plus YR tan beta L whole square. So here this value becomes ys is equal to yr of, here j square is there, j square is equal to minus 1, minus value, minus into minus plus, so that's why, so here note down this, j square is equal to minus 1. So here yr of 1 plus tan square beta l plus j tan beta l of 1 minus y square by 1 plus yr tan beta l square. But here ys is equal to gs plus j bs. So let ys is equal to gs plus jbs. So here gs real part and bs is the imaginary part. So in the above equation ys is equal to yr of 1 plus tan square beta l plus j tan beta l of 1 minus y square by 1 plus yr tan beta l. So in this real part gs is equal to yr of 1 plus tan square beta l by 1 plus yr tan beta l whole square. So imaginary part bs is equal to tan beta l of 1 minus y square by 1 plus yr tan beta l whole square. Here let ys is equal to gs plus jbs, then equating real part and imaginary parts, then gs is the real part and bs is the imaginary part, equating real parts equal, then gs is equal to yr of 1 plus tan square beta l by 1 plus yr of tan beta l whole square, and similarly imaginary part bs is equal to tan beta l of 1 minus yr square by 1 plus yr tan beta l whole square. So here for the condition, this condition for maximum power transfer theorem or for maximum power transferred from source to the load, the place of stub at which the total susceptance must be equal to 0, the total susceptance. So this is the imaginary value is known as susceptance value. So here this is the transconductance value. So gs is the real part value. Real part value must be equal to 1, and imaginary part susceptance, the total susceptance at the place of stub must be equal to 0. So that's why for this condition is, if this condition is satisfied, then the maximum power is transferred from source to load, and there is no reflections of the signals. So that's why the signals are easily traveling to the load. So this condition is satisfied. So the condition is 1 plus j 0. So here real part equal to 0 and real part equal to 1 and imaginary part equal to 0. So that's why real part gs equal to 1 and imaginary part bs is equal to 0. So here gs this value must be equal to 1 and bs this value must be equal to 0. So then here gs value must be equal to 1, real part must be equal to 1, then yr of 1 plus tan square beta l by 1 plus yr of tan beta l whole square equal to 1. So then this value equal to this value, 1 plus yr of tan beta l whole square is equal to yr of 1 plus tan square beta l, then 1 plus yr of tan beta l whole square is there, so that's why yr square tan square beta l 1 plus yr square plus tan square beta l is equal to yr into 1 yr plus yr into tan square beta l. So then tan square beta l taken into one side and other side yr minus 1. So then y square tan square beta l minus yr tan square beta l is equal to yr, this my 1 is goes to this side, minus 1. Then we have to take yr tan square beta l is common, then the value becomes yr minus 1 is equal to yr minus 1. So then this value becomes that side, then yr tan square beta l is equal to yr minus 1 by yr minus 1, both are cancelled, is equal to 1. Is equal to 1. So then tan square beta l is equal to 1 by y. So but yr normalized form into convert into the that value is equal to yr is equal to yr by y naught. yr by y naught. Then so tan square beta l is equal to 1 by, in the place of yr we have to substitute yr by y naught. Then y naught becomes into numerator. Then that value becomes y naught by yr. So then tan beta l is equal to square root of y naught by yr. So here tan beta l is equal to square root of y naught by yr. Here in the place of l is the length of the stub, that length of position of the stub. Here l equal to position of stub, that is l suffix s. In the place of l we have to substitute l suffix s. This is the position of stub. And then tan beta ls is equal to square root of y naught by yr. So bl is beta into l is equal to tan inverse of square root of y naught by yr. So ls is equal to 1 by beta tan inverse of y naught by yr. But beta is equal to 2 pi by lambda. So that's why in terms of lambda, ls is equal to position of stub is equal to lambda by 2 pi into tan inverse of square root of y naught by yr. In terms of this is the position of stub in terms of admittances. But in terms of impedances, then that is equal to y naught is equal to 1 by z naught, yr is equal to 1 by zr. Then the value becomes ls is equal to position of stub is equal to lambda by 2 pi tan inverse of square root of zr by z naught. This is the equation of position of stub. This equation is the location of the stub. This equation gives the location of stub. Now the susceptance at the point of attachment of stub is given by susceptance. Now we have to find out the susceptance. So here now the susceptance at the point of attachment of stub is given by Br. Why? Because here we are normalized. This is the normalized admittance. So we have to convert normalized into the original admittances. Then Br, this is the real part, imaginary part Bs, basically imaginary part Bs, but this form is in the normalized form. That's why we have to maintain first normalized imaginary part Br, B suffix r, that is equal to Bs by y naught. That is equal to tan beta l of 1 minus yr square by 1 plus yr tan beta l square. But tan beta l, in the derived equation, tan beta l is equal to square root of y naught by yr. So in the place of tan beta l we have to substitute square root of y naught by yr. Then the value becomes ps by y naught is equal to square root of y naught by, in the place of tan beta l we have to substitute square root of y naught by yr of 1 minus. So this is converted into the original form. Then y or normalized yr converted into original form, that is yr by y naught whole square by 1 plus yr. In the yr into tan beta L square is there. So that's why y r square tan beta L square. So in the place of y r square we have to substitute y r square by y naught square, and tan beta L in the place of tan beta L we have to place square root of y naught by y r square. So then the equation becomes square root of y naught by y r 1 minus y r square by y naught square by 1 plus y r y naught. Here row 2 square both are cancelled. Then the value becomes y r square by y naught square into y naught by y r. Y naught square cancel, y r square cancel. So the remaining value here by y naught is equal to square root of y naught by y r of y r square. Here y r square is there. Here y naught square minus this value becomes y naught square minus y r square by y naught square by 1 plus y r by y naught. So this equation becomes so here bs by y naught is equal to square root of y naught by y r, that in of y naught square minus y r square by 1 plus y r by y naught into y naught square. So bs by y naught is equal to square root of y naught by y naught square minus y r square by y naught plus y r by y naught into y naught square. So square root y naught both are cancelled. The equation becomes bs by y naught is equal to square root of y naught by y r of y naught square minus y r square by y naught plus y r. So y naught both are cancelled. So therefore bs susceptance value at the position of stub is equal to square root of y naught by y r. So here y naught square minus y r square, a square minus b square, that is equal to a plus b into a minus b. So that's why y naught plus y r into y naught minus y r by y naught plus y r. So y naught plus y r both are cancelled to each other. The remaining value ds is equal to square root of y naught by y r of y naught minus y r. This is the susceptance value at the position of stub. Now we have to find out the length of the stub. Length of stub. So hence so in order to find out the length of the stub, the main equation is the fundamental equation is Vr is the load voltage. Load voltage is equal to Vs cos beta L minus J Z0 Is sin beta L. So for the lossless short circuited stub, Vr is equal to 0. Then we have to substitute the 0 in the place of Vr. Then the equation becomes 0 is equal to, and in the place of L we have to substitute L suffix t. L suffix t is the length of this stub. So we have to find out length of this stub here. So that's why 0 is equal to Vs cos beta L t minus J Z0 Is sin beta L. So here ZT short circuited stub impedance, that is equal to Vs by Is is equal to J Z0 sin beta Lt by cos beta Lt. Sin by cos is equal to tan, that is equal to short circuited impedance of stub, that is equal to Zt is equal to J Z0 tan beta L. But it is converted into admittance, short circuited admittance. Then Yt is equal to 1 by Zt. Then the value becomes 1 by J0 tan beta Lt. This value becomes, then the value becomes 1 by J is equal to minus J, 1 by Z0 is equal to Y0, 1 by tan beta L is equal to cot beta Lt. So the short circuited admittance is equal to yt is equal to minus j y naught cot beta lt. But it is complex conjugate, complex value. So real part plus imaginary part. Yt is converted into the complex value. Then yt is equal to gt plus jbt is equal to this value minus j y naught cot beta into lt. So here real value, there is no real value. Gt is equal to 0, bt is equal to imaginary value, bt is equal to y naught cot beta lt. Then so here gt is equal to 0 and bt is equal to, here yt is equal to gt plus bt. In this value yt is equal to only minus j y naught cot beta lt. So that's why here only present imaginary value, real value must be equal to 0. So that's why real value gt is equal to 0 and imaginary value bt equal to minus y naught cot t beta into lt, where lt is the length of the stub. Now at the point of attachment of the stub, the sum of line susceptance and main line transmission line susceptance and the stub susceptance must be equal to 0. So then when these two susceptances are must be equal to 0, then it is possible to maximum power transfer from source to the load. That is the condition. That is the condition at which only we have to place the stub. So for the impedance matching. So that's why Bs plus Bt is equal to 0. So in previous equation, Bs is equal to square root of y naught by yr of y naught minus yr. But here Bt is equal to minus y naught cot beta l. So these sum of these two equal to 0. Then the equation becomes square root of y naught by yr of y naught minus y naught cot beta lt is equal to 0. Then the equation becomes so here this equation is square root of y naught by yr of y naught minus yr minus y naught cot beta lt is equal to 0. So here y naught square root of y naught by yr into y naught minus square root of y naught by yr into yr minus y naught cot beta lt is equal to 0. So we have to take y naught is common. Y naught to take is common. Square root of y naught by yr minus y naught is common. So that's why minus cot beta lt is equal to, so then this value goes into that side, then plus square root of y naught by yr into yr. So then the equation becomes square root of y naught by yr minus cot beta lt. So then equal to square root of yr by y naught by yt yr into yr by this value y naught. So this value becomes y naught square root of y naught into yr is equal to square root of into yr into square root of into yr. So similarly y naught is equal to written as square root of y naught into square root of y naught. So then square root of y naught, square root of y naught, square root of yr cancel. Then the equation becomes square root of y naught by yr minus cot beta lt is equal to square root of yr by y naught. So then cot beta lt is equal to square root of y naught by yr minus square root of yr by y naught. This equation becomes cot beta lt is equal to y naught minus yr by square root of yr into y naught. Then the equation becomes, so here this equation becomes tan beta L t is equal to square root of, in terms of tan beta L t is equal to square root of y naught yr by y naught minus yr. So beta L t is equal to tan inverse of square root of y naught yr by y naught minus yr. But beta is equal to 2 pi by lambda. So here lt is equal to lambda by 2 by tan inverse of square root of y naught yr by y naught minus yr. In terms of impedances, this is the equation in terms of admittance, but in terms of impedance, the length of stub is known as that becomes LT is equal to lambda by 2 pi tan inverse of square root of zr z naught by zr minus z naught. This is the length of the stub. This equation is length of the stub equation. Here the disadvantages of single stub. So single stub it is used for fixed frequency only, and second one is it is not suitable for coaxial cables. So why? Because for the coaxial cables drilling is needed. Drilling the holes to put the holes on the top layer of the coaxial cables, drilling is needed. So it is not suitable for coaxial cables. So third one is it is useful only for the open wires, and it is not suitable for matching variable impedances. These are the disadvantages of single stub. Thank you. The topic single stub is over, and for daily classes and for any updates, subscribe my channel. My channel name is Electronics for Gate by Kota Venkanna. My mobile number is 630-5826-909. Thank you.